All right. By this time, good afternoon. Normally I can't say good morning or good afternoon, but since we had a little delay here, good afternoon. Okay, so sorry about that connection problem with the HDMI cable. Maybe I bent it too much on accident right before we got going. I don't know. But replace that. We're good now. We've got the attendance thing. Did that work? You guys work with it? Okay, great. For now, my policy at the moment is going to be I'm going to put this up here. Don't bother sharing it with anybody because just tell them to go to the YouTube channel. Don't be lazy. So if somebody has to miss class, I'm leaving it open for the day. So that's on you to participate in at least going to the channel, finding that, entering it, and participating in that. The rest is up to you for being an adult, whether or not you actually listen to the lecture and do what you need to do. And again, most of the credit for the class is coming from, performing well on the exam. So you probably need to do that, but at minimum, you have to take some action. So you can tell your classmates to shove off and go to the link, do their homework, so to speak, for 2 minutes. At the moment, I'm not going to bother too much with, making this really difficult or painful, but I'll put this up here at the start of class, at least for a minute or two, to get going. So maybe I'll change that, but I'll let you know. And at least for the beginning, LSU has asked us to collect attendance for everybody within the first couple weeks for some reporting things, financial aid kind of stuff. So that's important for that matter that you've done this. So if you haven't done it, please do so. And then, like I said in the past, next week, since I'm doing some review stuff that not all of you really need to be here for, and some of you might be adding, dropping, just for my own sake as well as yours, I'm going to keep it simple and not record any attendance in terms of grades until after next week. So that's the deal. Okay, so with that, we can get going to our lecture and pick up where we left off. I had mentioned this problem. And by the way, as you saw, we had some technical error. If I have a situation where I'm not able to do my normal lecture stuff, it feels bad on my end because I do a lot on my laptop for you. So if that connection or maybe the Wi-Fi is out for the day or something, that kind of sucks. You won't have this particular lecture online, and I don't have a whiteboard with all my notes, ready like I normally do. I'll make the best of it, perhaps make a shorter lecture, but I do have fairly equivalent sections of these lectures online, so you could look at past semesters. So if that were to happen, I would upload old notes that are very similar and give you kind of a short version in class if we have to. So just so you're aware, that's my plan if the IT issues are bigger than this. All right, so we left off last time with this example from our book. We've got this stream. I told you that, hey, this is going to be a very simple mass balance, but at first you might be, hey, word problem, how do I do this? I don't know how to do this. I've not looked at this kind of thing for a while, or ever maybe. So I wanted to give you a quick picture, now that you've had a little time to think about it. Given our delay, I'm not going to give you more time to think about it necessarily, but I'm going to walk through it at a high level, and then we'll come back to this problem towards the end and just solve it properly so you can kind of see how the pieces that we learned today are going to fit into it. So the problem says we have a stream that's flowing at 10 cubic meters per second, and it has a tributary feeding into it with 5 cubic meters per second, so half of the flow rate. And they each have some concentration of chloride. By the way, chloride is Cl-. That's the ion of chlorine, just one chlorine atom with a -1 charge. So that's in there. That stuff's not very reactive. That's part of what's in table salt. So whenever you're cooking and add some salt, you've got some chloride. Okay, so these are joining and they mix. It's not reactive. That's what it means when it says it's conservative. And assuming they mix completely, the two streams, we want to know the downstream concentration. So the question is, what is the concentration of the mixture coming out? So like I said, I'll give us more space to solve it, but one thing we could do up front is to kind of take a look at the two different inputs. We have input 1, it's going to combine in some way with input 2 and give us that output. And if we take a look at the units, well, first of all, we've got two questions. One is what's the flow rate going out, and one is what's the concentration. So we're going to build the precise way to solve this in a minute, but just intuitively, you might say to yourself, okay, well, what all's going in? We can take a look at the units that we know about going in. If this is 1 and this is 2, we could say, all right, there's 20 milligrams per liter and there's 10 cubic meters per second. Maybe we need to combine those in some way. (10 cubic meters per second). And on the other input would be 40 and 5. Don't need to, not dividing here. Okay, and so then in the output, we have to solve for something, and really what the question asked for is the concentration. And what we notice is that a concentration should be in milligrams per liter. We'll elaborate on that, because we'll talk about concentrations and things in a minute. So what it looks to me like, just looking at kind of the units and where the stuff is, if we can figure out the total milligrams per liter on the left per, let's say, volume over time, then we can find the same on the right. So chances are good that we'll need to solve for that Q of the combined flow. That's going to be pretty easy just looking at it, right? We're not given any other information about sources or sinks of water. So 5 plus 10 is 15, right? So the Q, the flow rate, Q is often used for flow rate. And we will often use that for that purpose in our class. That's going to be a volume per time. So to get this Q of the mixture should hopefully be easy to see that that should be 5 plus 10, right? 10 plus 5. Now that we have that, all we need to know is how to relate our flow rates and our concentrations. And if you stop and think about it, if we have some concentration, what we're really looking for at the end of the day is how much mass, or in this case concentration, of our stuff that we're interested in is moving around per time. Almost the whole class will be focused on some version of mass per time, okay? As an accumulation rate, as maybe we make a reactor to say we don't want the mass per time to be changing. We want to kill enough of the stuff, or destroy enough or grow enough of the stuff so that that's steady. And so it's a constant amount doing the action that we want. So we'll talk about things like steady state or non-steady state, referring to are we accumulating things or are we having just the same amount over time? So mass per time, and if we take a look, we can get to mass per time if we notice we've got mass in milligrams, we've got volume, liters, and then in our flow rate we have volume and time. So if we put those together in a way that gives us mass per time, we'll have something that's a mass per time 1 plus mass per time 2 is equal to a new mass per time for the output, right? So I'm now kind of taught the lecture in some way. That's our mass balance. That's what we need to do. To get to mass per time, we can simply take the flow rate, which is volume per time, and multiply it by the concentration. So I'll write this out a little more explicitly here. I'm just going to write this over here. So flow rate, which is volume per time, multiplied by our concentration, which is mass per volume, will give us a mass per time. Okay, this is not the only way to arrive at a mass per time, but this is going to be the most common one in our class. A volume times a flow rate times a concentration. So we're going to see this a lot. Q times C. All right? So in our case then, we can take the flow rate times the initial one, plus the flow rate times the second flow rate times the second input, and combine that with a full flow rate and the final one. So what that would look like would be Q1 C1 plus Q2 C2 yields this Q mixed C mixed. Okay? And we solve for the unknown. All right. We will loop back to that and put in the numbers and give us our final answer towards the end of the class. And you'll see kind of how we build to that from this principle of conservation of mass. So there's, in these types of problems, maybe you could have intuited that's what it's going to look like from this problem, even if you'd never heard of the term mass balance. Right? It's a word problem. It's possible to kind of figure that out. This is the type of thing that if you have done some chemistry labs recently, you've probably mixed some volumes and concentrations and had to figure out, okay, how do I get half a mole per liter when I started with 3 moles per liter? What's the concentrations? Things like that. If you haven't touched it in a while, you might be like, oh shoot, what am I doing? It's all simple algebra at that level, and you'll get there. It's just a matter of reminding yourself, okay, this is what we're dealing with the concentration. Okay, so to my soapbox on units. When we're dealing with any of these things, if you've not already noticed, the units are going to be very important. In fact, you might have noticed that I didn't even mention the fact that we had volume in liters and volume in cubic meters. So in certain cases, that cubic meters might cancel one another, and that will be the case we'll see as we finish that solve. But in many cases, we might say, all right, how many of these 1 liter bottles does it take if I need to treat 3 cubic meters per second, right? We might do some conversion that we do need to make that conversion. So we need to pay attention to them. We will deal with all sorts of different units. That's actually a large part of the challenge in this class, is just attending to the units, attending to what we are actually doing when it comes to a physical presentation or the reality of the situation. That'll give us the tools to properly balance our conservation of mass equations. Units are also great in case you forget how to solve a problem and you're sitting on the exam and you're like, well, shoot, I don't remember what this equation means. I don't remember which variable's which. Well, if you can remember the units on a few of the numbers or pick them up from the problem itself, maybe you can use process of elimination and say, this has got to be in meters per second if that's in cubic meters per second, right? You can help yourself by thinking critically about the units. Okay, I already mentioned, but almost all of our mass balances are really going to be mass per time at the end of the day. Sometimes we might use concentration per time and leave it that way, but what we're referring to is the rate at which some thing is changing over time. Said last time, sometimes we'll use number, like number of bacteria, something like that. We're going to just, for now, call that a mass balance still. When it comes to chemistry, we're basically doing the same stuff. It's almost all also a mass balance, and the purpose of the chemistry that we're doing is to understand where that mass is going, how it's being transformed, what state it's in. We're not going to do anything fancy to predict some product of a reaction that is unknown, or organic chemistry, not really going to touch on that much. We're going to keep it focused on allowing us to track the mass balances. There is a bit of chemistry we need for that because things like pH affect what chemical state our chlorine is in, for example. So we can't properly solve a chlorine disinfection problem if we have no understanding of pH. Okay? We're in a water and wastewater treatment class. I feel you need to be able to solve a disinfection problem involving chlorine. So you're going to have to suffer some chemistry even if you hate it. But it'll be okay. Even the chemical equilibria, which we're going to cover in more depth next time, that's essentially a mass balance. And the equilibrium equation is telling us in what state is our chemical. All right, so there are some expectations. I expect you to know SI units. We're going to use a lot of them, and they're the SI prefixes, like what is a kilogram or a kilometer, right? You should know that's 1,000. There's a few maybe you haven't used a whole lot. So if I give you micro, I hope that you will know, and if you don't, you'll study so that you will know, that's 1/1,000,000th, right? So 1/1,000,000, a microgram is 1/1,000,000th of a gram. Milli is 1/1000th, and we might even deal with nano, which is 1/1000,000th. So those are, the easy way to write that would be, you'll see over here, if a gram would be 10 to the 0, then a milligram, and also I expect you to recognize the abbreviations too. A milligram is mg, lowercase mg. That would be 10 to the -3, so we're going to do 3 logs or 3 decimal places over. A microgram, if I can find my microgram with a little mu, would be 10 to the -6, and a nanogram would be 10 to the -9. Okay? We could do a kilogram, 10 to the 3 grams, and so on. Bless you. So, I expect you to know those guys. If you don't, remind yourself, refresh your memory. Another point about units, you're going to be inadvertently tested because I have this nice table for you I'm putting on your formula sheet. I'll bring that up while I'm talking about it. And it just so happens that this table, and I'm not doing this to intentionally torture you or anything, but it's got important unit designations that include something that could be confusing. So if you look up here at dynamic viscosity, I want to draw your attention to the fact that there's a 10 to the -3 written into the units. Okay? So I'm telling you up front, I'm not trying to make it a trick question, but if you don't pay attention to the units, you might make it a trick question on an exam. Okay? If you do, I'm not counting off a ton. I'll explain that later, but I'm mostly wanting to see that you have the process right. If you get something like this wrong, it's wrong, but you're not getting full credit off. So pay attention to the times 10 to the -3 in the unit, right? So sometimes it makes sense to plot a graph that way, make a table that way. This is part of the unit here. So if we were to check the dynamic viscosity at, let's say, 0 Celsius, that should be 1.781 times 10 to the -3 kilograms per meter per second. That's the dynamic viscosity of water. Okay, so that's something to keep in mind and to watch out for, particularly on this table, but really anytime you are dealing with units, it's going to be important. Okay, so let me pull up for you our table. Of course, Adobe thinks I want to try new updates and gives me 10 different hints to start. All right, so on the exam, you will have a periodic table. This table that we just looked at on the slide. This gives you, really what we're going to use is density and dynamic viscosity. I don't think we'll typically use any of the other pieces. So density, dynamic viscosity per temperature, right? Those are the 2 pieces that you'll really need. And then you'll have a formula table. And I'll just build this out as we go along, so we'll add more to it. But for now, these are the formula you will have and potentially need for your first exam. So that's already posted to Moodle. Should be able to see that. Good idea to, as we go along and you see these, to study and make sure you're comfortable with them. Okay. So a few unit conversions I expect you to memorize. And these are, I'm expecting you to memorize a few of them because they are so commonly used. in our processes here. You probably have your own that you'll know over time just from your own experience. For example, you probably know there are 12 inches in a foot, right? How do you know that? You just kind of know it, right? That's experience, right? So I'm asking you to make sure you either have the experience or study a few of these to ingrain that, because you'll need to know that it would take 1,000 1-liter bottles, and this is a 1-liter bottle. If you ever get a little confused as to, okay, how big is a liter compared to a gallon? Well, just remember my little blue water bottle here, right? And then think of a gallon jug of milk. Then you can think to yourself, okay, it's going to take a few of these, but not hundreds of these to get to a gallon. Now, I'm not asking you to remember the gallon thing, but I am asking you to remember that there's 1,000 of these per cubic meter. So if you think a meter's a little over 3 feet, you do that 2 sides and then a cube. Okay, 1,000 sounds reasonable. It's probably not 10. Don't think 10 of these would fill that. And I think you don't need, 100 million of them, right? So use a little bit of your intuition. If you forget, you can probably make an educated guess just glancing up here at my water bottle or your own. All right, so 1,000 liters in a cubic meter. Another useful one is there's 1 milliliter in 1 centimeter cubed. Now this sounds weird because we just went from 1,000 liters in a meter to now 1 milliliter in a centimeter. The deal is, when we convert volumes, we have to cube the units. So if we were to say, 1,000 liters in 1 cubic meter, well, 1 milliliter is 0.001 liter, and we want to know in how many centimeters. We'll do it this way. Yeah, that's fine. Well, what we have to do is we have to say, if we start with 1,000, I'll do it over here, 1,000 liters in 1 cubic meter. Well, it turns out if we want to put that into centimeter cubed, we would need to say 0.01 meter, and cube both the 0.01 and that meter unit to convert. So I'll make this a little more clear. Sorry. We'll do it this way. We'll say 1 centimeter is equal to 0.01 meters. And so 1 cubic centimeter is equal to 0.01 meters cubed. Because we actually cubed the 1 here too. And 1 cubed is 1. So just a little math reminder here that if we're converting these units, 1 cubic centimeter is equal to a lot fewer cubic meters, right? Than the translation goes. We cube that conversion. Okay, so anyway, one easy thing, you could do all that math by yourself and figure it out if you need to, or you could just memorize that it's 1 milliliter per 1 centimeter cubed. Okay, it turns out that that's also very handy. So if I ask you how many grams is equal to 1.000 kilograms, let's use they were saying 1,000, okay? 1,000.0 kilograms per cubic meter, okay, at 5 Celsius. So take 2 minutes and see if you can solve that problem. How many grams in 1 milliliter of water? Some of you who have already memorized this don't even need to solve anything. And that's part of my point. Okay, so you see where this is going? Kind of got a feel for it? Probably a few of you didn't need to solve because you just remember maybe you worked in a lab already and calibrated a pipette tip or something, before. Well, it turns out at 5 Celsius, we have this nice even density. It should be 1 gram for every 1 milliliter of water. There's probably a few ways you can approach this, but that's a nice definition or nice fact to keep in mind. My 1 liter of water is 1 kilogram. Now, I've drank a little bit of it, but the bottle weighs a little bit, so maybe this is 1 kilogram. And for reference, 1 kilogram, I mean, you could heft it and feel, but it's about 2.2 pounds for the imperial reference. Okay, so that's a good one to keep in mind. So we can see if we have essentially refrigerator temperature water, then it's going to be 1 kilogram per liter, or that would translate to 1,000 kilograms in a cubic meter, and so on. All right, so that's a few basics I'd like for you to keep in mind. I'm not asking a whole lot, but you should be comfortable with those so that that's not your challenge on an exam, okay? If I do ask you for something else, maybe I'll ask you to solve a problem where we are given a more typical value that, let's say, a wastewater treatment plant might use in the States might be how many million gallons per day. Okay, so there we have, instead of cubic meters per second, we're doing gallons and days, right? So we might do some sort of conversion like that, but I'll give you the conversion, or maybe it's a homework and you can look that up. Okay, so moving on a little bit, I'd like to talk about a few different conversions and then concentrations. So number to mass conversions are going to be an important one. Specifically for chemistry, this is the concept of moles, but hopefully I can convince you today that it's not as scary as you remember from like high school chemistry, if that's the last time you saw chemistry. So number to mass. Essentially, we are providing a ratio. So if I tell you how many eggs are there in a dozen eggs, you would say, a dozen, you dummy. Yeah, 12, right? And maybe we could be fancy and say a baker's dozen, then it's 13, right? That's a little, I don't know where that comes from. But so one for the baker, I suppose. So it's 12. I could ask you the same exact thing about how many molecules are in a mole of water. How many water molecules? There would be, instead of 12, it's a different number. It's just a big number. That's Avogadro's number, 6.02 times 10 to the 23rd. So when you see a mole, just think dozen. Okay? It's just a little bit of a different number, but it's the same concept. How many dozen molecules are we reacting? And that becomes important, and I'll elaborate it, but we just need to make sure we can translate from number to mass. Because I could have a dozen cars, it's going to weigh something very different than a dozen eggs, right? Obviously. It's a big duh thing, right? It's like you don't even have to say that. But when it comes to molar units and molar conversions, if you haven't seen chemistry in a while, and then maybe it scares you, that's the same deal. And that's why we need to relate with it. Because sometimes we're doing a reaction that involves not mass, but number. Okay? And sometimes then we need to say, well, how much mass do we have to add to get that reaction with the right number? So we have to go back and forth between them sometimes. Am I strong enough to carry a dozen eggs in from the grocery store? Yes. How about a dozen TVs? Not all at once, right? That's a very different equation. So even a dozen gallons of milk would be quite the challenge. That would be probably too much. Okay, and it would certainly rip the grocery bags. All right, so concentrations. We'll come back to moles and all that in a moment. I just want you to be aware that it's unit conversions. That was kind of my point there. We will do unit conversions with mass and number, A lot of times that'll be with the molar conversions. Okay, concentrations. I started the class by saying we care about stuff in some other stuff, right? So technical, so fancy. That's a concentration. We're saying we've got some mass of particles in some volume of air, or some number of molecules in the soil that has a bunch of water in it, right? It's a mass or number or some quantity per some other quantity. Sometimes with gases, which we're not going to deal with too much, but we might say we have some volume of that gas per total volume in this room, right? We have some volume of carbon dioxide that we're breathing out, and it's just ambient in the room, per volume of the room. So sometimes we say volume per volume. Maybe in gases we might do pressure. Sometimes we say parts. And as we'll see, that's a lot like percentage. Okay, so we might do volume. Let's talk about denominators first. So volume is a common one. That's the one we're primarily going to use. Something like grams or milligrams per liter, quite common. Maybe kilograms per cubic meter. Sometimes a percentage by volume. We'll do, we could do mass as a denominator. And again, if we have 1 liter being 1 kilogram, okay, we could maybe use kilograms of water as a denominator, and that will look a lot like our typical milligrams per liter. Of course, that changes a little bit with temperature, so not very convenient. So typically we'll stick for our water cases with per liter, but maybe you're doing soil and you do mass of something per mass of soil. Okay, those types of concentrations do exist, and we might see them at some point. Parts per X. You might have seen parts per thousand, parts per million, or maybe just ppm, maybe ppb, parts per billion. If you haven't noticed, well, next time you're watching something that's talking about air quality or reading something, you might say, oh, hey, I've seen that. And sometimes we use it in water as well to say, all right, there's some number of ppm of lead in this contaminated water. What that's referring to is actually something you're very familiar with, but you might not have realized it. So parts per million is like saying percent, except percent is parts per 100. Okay? So all you have to do to convert and use it the same way as you would with a percentage is to recognize that that denominator changed. Okay? So percent, if you spell it out, per, we use per a lot. It's like, that's kind of obvious. How many for each kind of a thing. Cent is the Latin root for 100, right? So it's literally saying, when we write percent, it's essentially implying parts, how many of the 100. So if I had 100 water bottles and one of them is blue, I have 1 part per 100, 1% of them is blue, right? So that's something you've dealt with for a long time. You know how to deal with that. Now, if we do per 1,000, that would simply be how many per 1,000. Okay? So to convert from, let's say, 10 parts per 1,000 into 10%, you could multiply it by 10 to get rid of one of the decimal places on the bottom, and now you're into percentage. Okay? You'll be able to deal with this if you need to. I just want to show you that's how this particular type of unit works. It's a percentage, except it's got more digits. Sometimes people will even write parts per 1,000 with 2 little zeros on the bottom of a percentage sign. Okay? Just implying it's got that one extra zero. We're not really going to deal with them too much, but if you see it on a homework, or maybe I put one in on an exam, that's something I try to remind you, hey, you know, parts per million, effectively, this would be like a milligram per liter. Turns out that works out approximately like that. I'm not asking you to memorize that. I would probably try to remind you if it was relevant. Anyway, I want you to be familiar with the fact that concentrations in general, this is how we deal with them. And what's important is, the first thing that's important really is the denominator. But of course, we can change the numerator as well. So on the numerator, we would often use mass, milligrams of chlorine, for example. Sometimes we'll use number. And this is coming back to what I was talking about with a dozen eggs and a number of molecules. And so the big question here is, how many eggs does it take to properly egg a car? Which I'm not advocating. If you try, I hope this happens to you, this guy over here. Because vandalism is not so good, right? But you would think to yourself, all right, maybe I'll buy a dozen eggs and that'll be enough. But is that a dozen eggs per dozen cars? Is that 1 pound of eggs per 1 pound of car? You might think to yourself, a car weighs 2 tons or 1 ton or something, right? 2,000 pounds. Does that mean I need approximately 2,000 pounds of eggs? Probably not. Maybe 1 dozen's enough if you're trying to do a thorough job and get every handle and windshield or whatever, Not giving you any stupid ideas here. So a mole is 6.02 times 10 to the 23rd of molecules to work with, all right? So just try to remember this if you're having some pain thinking about molar units, right? It's how many of this corresponds to the right amount of mass, or how much mass would give us the right amount, because some reactions require a number per number basis, right? Maybe it's, I don't know, eggs per door handle or something. It's not mass. If you try to get a ton of eggs, like a literal ton, that's not going to work out so well. So think of a dozen of X as 1.2 times 10 to the 1. 1.2 times 10 to the 1 is 1 dozen. Okay? You've never written it that way, but maybe it's worth writing that out just to say to yourself, oh, okay, I can handle this mole thing if I can handle a dozen, right? Okay, enough about that. Getting into these molar units, when we refer to a mole of something, grams per dozen, okay? So if you just write dozen, maybe it won't scare you so bad. And just remember that you have to, if you are being technical about it, you need to change the number, right? Just call it a mole instead. And you'll be perfectly fine. Okay, so I say all of that to really highlight and remind you that sometimes we need to account for the number when it comes to chemistry. This is how we do it. You've seen this before at some point. I hope this is the simplest you've ever heard it and most straightforward. We will then go on and use molar units. When we say some number of moles per liter, you could also say that as, let's say, 2 molar. The capital M being the abbreviation for moles per liter. That would be a molar concentration. So the other thing we use concentration-wise is we use these brackets to say, if I put brackets around X, that means there are, we're talking about the moles per liter of X. Okay, so if I say X equals 0.001, we should know the units have to be capital M, which is the same thing as writing moles per liter. We could then, if we want to be change it a little bit, we could say that's also equal to 1 millimolar. That would be fine too, or 1 millimoles per liter. Those are all just simple unit conversions. The brackets designate and say this must be in moles per liter. So if you see brackets, we're talking dozens, not tons. Okay? We might need to change this into mass, into milligrams or grams, but do not take the brackets and associate that with a mass unit. Okay, you have to do a conversion if you see the brackets. Or rather, if you see the brackets, you are not in mass units. So if you need a mass, you need to do a mass conversion. Okay? So we do have some formula when we do equilibrium. It's on a numbers basis, and we have to do that. We will have some problems when we get to the chemistry stuff to say, okay, we want to add X amount of chlorine, like physically some mass of it. So how much do we need? Well, we have to figure out the number, molar units, to understand the chemistry and then put it back into mass. So we will have to go from mass to moles back to mass. There will be some problems like that. That's just the nature of it. Hopefully, with this approach, you'll be all right with that. Okay, another type of unit that we will find is number units. I guess another take on number units. So moles are a number unit. But kind of a separate category will be when we're talking about disinfection or maybe some particles in water, where it's much more handy to count them, much more convenient to count them than to weigh them. It's pretty hard to weigh a virus. It's a lot too small for that. So we will use number concentration sometimes, where the numerator is some number. We have 10,000 bacteria per milliliter, something like that. So we will often use N as a number per volume instead of C. C we often have as some concentration in mass units. That's just typical. It's just the convention I'm going to use. It's the convention the book uses. It's handy. There's no reason you couldn't use C as a number concentration. I'm just letting you know that my convention will be, if I'm doing an uppercase N, I'm most likely, very likely, using some number-based concentration unit. I'm excluding moles here because I'm specifically talking about like counting germs or particles. Okay, so this is going to be that type of number. Something like colony-forming units for bacteria, we might put them on a little petri dish and count how many form little colonies, so we can visibly count them. For viruses, we do the similar thing, and they form little plaques. I could tell you more about that if you're curious, but that would be CFU or PFU per liter is typical units. That's a number of bacteria or viruses per volume. Maybe we'll see often CFU per milliliter. We could use liters, we could use milliliters. Some standard tests use 100 milliliters because that's, you filter a little bit of water and that's sufficient to give you a good idea of the exposure if you drank a little bit, right? It's a pretty common test. Okay, when it comes to disinfection, we're typically comparing what we start with before we treat it to what we ended with after we treated it. So very often we will have N and N naught. N would be the final. Maybe we'll put a little T there to say N at some time T. Or if it's just blank, we just know that's after whatever happened. And the N naught is meaning the initial. So if you ever see on a disinfection spray can, Lysol or something, it kills 99% of germs. Well, what they're saying is not that they've tested every germ out there and it kills almost each one of them. They're actually saying, when we tested this on some germs, of those germs, it killed 99% of them within our little test. And I guarantee you they could get 100% that they are able to count if they just gave it more time or more Lysol. So they're just reporting some typical, okay, I take it, I wipe the counter with it, and then I test how many are left. So within whatever test they do, that's where they're getting their number. And that number is coming from some final versus initial. So if we had an initial of, let's say, we'll just say 10,000 germs, we'll say bacteria, colony-forming units per liter. If we have that, and then we end up with an N final of 100, Well, I could ask you, what is the percent removal? Okay, and what your brains are doing right now is trying to figure out, okay, where do I put these pieces to come up with a number, right? How are we exactly doing this? Which is why I'm going to show you the simple or the straightforward fraction removed versus fraction remaining. Okay, so if we take n over n naught and think about what that means, we can also do this math here in a moment, but that's how many remain compared to how many we started with. So this will be essentially the fraction remaining, is the simpler way to start typically. So this will say 100 over 10,000. We could just get rid of a couple ones or a couple zeros, and this should be left with 1 over 100, right? So that's 0.01. So if we're looking for the fraction remaining, this is n over n naught. A lot of times what we're trying to report or tell somebody is how many we removed, because you're not going to advertise and say only one germ is left. That's not a very compelling thing. Or only 100 were left. What? There's germs left? No, it sells a lot better. It means a lot more to us if we say how many are actually removed. So if we want to get to that, we can actually simply take 1 minus n over n naught. And I'm going to separate our stuff here. So 1 minus it, if we have some fraction that remains, that means the other portion is the stuff that was removed, right? So that's why we can just take 1 minus, because everything else was the stuff that's removed. So if that's our fraction removed, if this is 0.01, then 1 minus 0.01 in that example would be our 0.99. And if we multiply that by 100%, that gives us 99%. So 99% removal could be found from this little example here I'm giving you. The fraction remaining was 0.01. The fraction removed then is 0.99. That means we removed 99%. So when they do this experiment, they are counting how many are still there and then comparing that to how many they started with and doing this math accordingly. So there's a chance they used the easiest germ to kill, but they can still say it killed that many of them. I think there's probably some protocols they follow. I'm sure there are something there. But that gives you a picture of how this number comes about. And that's something we will use for our disinfection as well. Now, when we do that, one convenient shortcut to describe, sometimes we might say, or might need to say, oh, we killed 99.99%. That's a bit of a mouthful, and it's easy to get the digits mixed up. So another way to say that is that's a 4 log removal. Log talking about the fact that we are doing a log base 10, meaning 1 decimal place on a 10-based scale. It's quite convenient. So a 99% removal, that's a 2 log removal because we moved the decimal place twice to get there. Okay? So a log meaning a factor of 10 for every 1 log. The way we can get there mathematically, if we have the fraction remaining and removed here, I kind of already gave you this example ahead of time, but if we convert that to log and say the log reduction for a given removal, let's take the log of n over n naught. So if we take the log of 1 over 1,000 in this case, this would be a 3 log removal or a 99.9% removal. If we were to do that, and you put that in your calculator, that should be 0.001. Okay, I hope. That's also equal to 10 to the minus 3. So little shortcuts, little things maybe you haven't paid too much attention to lately. So the 0.001, I'm sorry, this should be, say, it's a 3-log removal. Sometimes we might even say if we're growing bacteria, maybe for wastewater or something, oh, it's a 3-log growth. That would be 1,000 times more than you started with, okay? It's just another simple, again, something you know, something I'm only telling you and refreshing your memory on because it's going to be part of the context that we talk about this stuff in the class. So hopefully a good and easy refresher there. All right, so let's get to mass balances. Mostly we're going to do this next time, but I want to give you the basics and take a look at that problem we started with. So mass balance, what we're looking at really is the accumulation within some defined container. So if we have this drawing and we say this, we can call it our control volume, meaning whatever's in there, something might be happening in there, different water might be coming into it. We saw this in the other problem, it looked kind of like that. Whatever is occurring, we are drawing our interest around this bubble. So we'll have something inside happening maybe, and we will track what's leaving and coming in. So we will have some inputs. We will have some outputs. I mean, I guess it's possible for us to have inputs and no outputs or vice versa. Most of the time with water, we're conserving water and we're not creating or destroying water. It's possible maybe to directly add mass, you know, shovels of some powder or something. That would be a way to have some input without a corresponding output in terms of volume of water. But usually we'll have inputs and outputs. And then maybe we'll have some reaction. This will all be occurring in some volume there. Usually we'll have some flow rates. And we don't create or destroy water out of nothing. So typically we'll have some concentration initial, some concentration final, just leave it as C, and a Q. So we're going to look at systems in this manner to try to understand what is the accumulation rate, what is the mass per time. Are we accumulating some substance within this control volume, or are we depleting it? So this could be a negative accumulation, or maybe that accumulation might be 0. And mathematically, the way to do that, to calculate that, this is our mass balance equation, the governing equation that we'll use. We're going to do all sorts of versions of this, but almost everything we do relates to this. It'll be setting that accumulation rate equal to the rate of inputs minus the rate of outputs plus whatever reaction rates are happening inside. That could be growth or decay. So this would be a rate of increase and this would be a rate of decrease, right? So with each one of these, each will be in a mass per time unit so that our ultimate mass per time unit, the units match. Okay, so we can have systems that we say are at steady state, meaning in that volume, we are not accumulating or losing a particular substance. This can happen even if we have a reaction creating or destroying that substance, because we might have more in the input and less in the output. In fact, that's usually what we're trying to do if we're treating water, right? We have a bunch of microbes, let's say, coming in, and we want for very few of them to be going out. And we want to design a process that does this effectively and continuously to the same amount, at least that amount, right? So usually when we're designing a process, we are aiming for a steady state where we get fewer stuff in the output compared to how much we have in the input, meaning we need a reaction in the middle to drive it down. So we have a reaction destroying it, and therefore the total accumulation can be 0, even though in our output there's less there. So that's what I'm referring to when I say a steady state. That would put our accumulation at 0. And if you look, if our accumulation is 0 and we have some in minus some out, minus some decay, just by writing that there is some decay and no growth, you can see with your eyes that the in has to be equal to the out plus decay, meaning out has to be smaller than the in, if there is any decay. All right? So that's going to be typical. It's going to be a very typical way to look at it. So we can say in equals out plus decay. We'll clear that up. So for disinfection, that's what we want. So that we have, if we have a lot of decay, the output, the number of bacteria leaving, is a small number. Okay? That's very typical, and that satisfies our steady state. Okay? So we'll get into more of the steady state stuff later, but let's apply that to this problem where we can find the inputs, the outputs, and for this particular problem, we said there was no reaction. Next time we'll talk about reactions. So I'm just going to solve this for you and speak through it as I go. So the inputs, we have CS, that's 20 milligrams per liter. And we need to multiply this by the flow rate there, the 10 cubic meters per second. We also have the CW at 40 milligrams per liter. I guess we'll say CS times QS and CW times QW. That'll be a little more clear. 40 milligrams per liter times 5 cubic meters per second. And if we add these two together, they have to equal the outputs. Okay, and the outputs being, so this would be, these two are the inputs. Here's the output. This would be the Q mixed times C mixed, which would be 15 cubic meters per second times our unknown. Okay, so we can take on the left side, 20 times 10 is 200. And the units here, by the way, are going to be milligrams times cubic meters per liter per second. We could convert the units if we wanted to, but we actually don't have to in this case because we're going to have these exact same units on the other side, and the cubic meters will cancel, and we'll be happy. So we'll see that in a moment. So we've got 200 plus 5 times 40 is another 200. Equals 15 cubic meters per second times some number of milligrams per liter. Okay, when we solve for that, anybody want to take 400 divided by 15 for me? What was it? 26.67. And just looking at the two numbers, we had 20 here and 40 here. And we are mixing those two streams where this one had a bigger flow rate. So I expect them to be somewhere in between. That certainly is between. Should be 26.67 milligrams per liter for our CM. Okay, any questions? Does that make some sense? All right, we'll see you on Tuesday next week. Happy Labor Day.